Welcome. The first speaker of this morning is Stephan Hartmann, and the title of his talk is Analogy-Based Reduction, a non-deductive model of intertheoretic integration. Please, Stephan.
Okay, yeah. Thanks very much for the invitation. It's wonderful to be back in Urbino and talk about this recent work of mine. It's related to the topic of the conference, but I broaden the focus a bit. Much of the philosophical work on analog models and simulations is on the topic of confirmation. I think another topic which is central in philosophy of science is also relevant for the discussion of analog black holes, and that's the topic of reduction. So I'm starting a bit broader. I will also give a case study which is not analog black holes to motivate my account, but I will then come back to analog black holes and talk about the topic of reduction in that case study. So the big picture is the following. Philosophers are interested in the question how scientific theories relate to each other, and philosophers like to discuss this topic by identifying extreme positions. That's what philosophers like to do. And here, on the one hand, we have the unity of science people, which is exemplified by this picture here from a famous paper of Oppenheim and Putnam. There is a hierarchy of levels, and each upper level reduces the lower level, and on top we have fundamental physics. So it's a very simple picture. The idea is, of course, composition or so, but it is meant to also hold for the theories that govern the particular level. So we have a strict order. It's all very simple. And on the other hand, we have Nancy Cartwright, who says that the only connection between phenomena is that they are part of the same empirical world. Yeah, that's exemplified by these balloons here, which are connected to the ground somehow. Yeah, so that's a position of radical pluralism. Yeah, Nancy Cartwright talks about the dappled world or so. But in my view, both pictures are way too extreme, and real science is somewhere in the middle. And I think it's not only that real science is in the middle, also ideal science is somewhere in the middle. So it's probably unachievable to get such a strict hierarchical picture, and the pluralism is also somehow against the spirit of science, which tries to identify connections between phenomena. So the job of the philosopher then is to identify interesting intertheoretic relations and to characterize these intertheoretic relations and also provide some kind of normative justification for them. That is, to answer the question, why is it good to have this kind of relation holding between actual scientific theories. Now, in philosophy, the starting point of this whole debate is intertheoretic reduction. So reduction is the paradigm intertheoretic relation. It's associated with the work of Oppenheim and Putnam, but then also came, of course, people like Nagel or so. So my goal is to understand how actual science works, not some future idealized science. I would like to identify different models of intertheoretic relations and not just the traditional reductive relation, which is sort of considered to be by some to be some ideal or so of an intertheoretic relations, and others, of course, hate reduction and think that it's bad and morally objectable and everything. Yeah? So the traditional model of reduction is Nagel's model of reduction. Ernest Nagel came up with it in the early 60s, published a whole chapter in his textbook, The Structure of Science, about it. What I want to do is I want to come up with a new model of reduction. So I think there is space for more models of reduction, not just Nagelian or Nagelian-inspired types of reduction, but other models of reduction. But also keeping in mind that reduction is only one type of intertheoretic relation. There may be others, looser ones, and philosophers should study them. So I propose what I call analogy-based reduction, which is a non-deductive type of reduction. And I illustrate it by looking at one of my favorite models, the Nambu-Jonah-Lassignew model. This is a model that was originally inspired by BCS theory of superconductivity in 61. And I'll show that on my model of analogy-based reduction, the Nambu-Jonah-Lassignew model is reducible to quantum chromodynamics, which is the fundamental theory of strong interactions. And then I'll revisit our case study of analog black holes, and I confront my model with it, and I will come to some kind of mixed conclusion as to whether analogy-based reduction obtains here or not. So this is the plan of the talk. I first speak about models of reduction, and in particular this elaboration of Nagel's original model of reduction as a contrast. Yeah, I then motivate that there's space for alternative models of reduction in the same spirit, and my twist will be a functionalist account. I will argue that reductions have certain functions in the research process, and then basically I argue if some model of reduction satisfies these functions, then it's a model of reduction. Okay, so part one, the generalized Nagel-Schaffner model of reduction. So the starting question is, what does it mean for a fundamental or phenomenological theory, TP, to reduce to a more fundamental theory, TF. So P stands for phenomenological, and F for fundamental. And Nagel's classical model tells us that a reduction or a reductive relationship between TF and TP obtains if TP is reducible from TF. Yeah, so it's a deductivist account, which was very popular at the time. Yeah, so you deduce the phenomenological theory from the fundamental theory. Now there are a couple of complications. In some cases, both theories share the same language, like when you look at Kepler's laws and Newtonian mechanics or so, it's the same language. These are homogeneous reductions, so you just deduce your theory from the other. And in other more interesting cases, the vocabularies are different. Yeah? So when you consider gases or so, you can use the language involving terms like pressure, temperature, volume or so, or you can use the language, I don't know, molecules traveling on trajectories with a certain momentum or so. Yeah, so these are different languages, and if you want to reduce one theory like the kinetic theory to the more fundamental Newtonian theory or so, what you have to do is you have to translate the terms somehow, and these are the famous bridge laws. Yeah, you connect terms from one theory to the other. And in that case, you identify basically mean kinetic energy of the molecules with the temperature. Yeah. In many cases, you also need additional auxiliary assumptions or so, but the ideal is that you can deduce one theory from the other. Now, Schaeffner made this model more realistic. He realized that exact derivation is often not possible. Yeah, he therefore introduced what he called a corrected theory of the phenomenological theory, TP star. And he then told us that it suffices if TP star can be deduced from TF, and TP star is somehow what he calls strongly analogous to TP, the phenomenological theory. So the idea is that if you consider statistical mechanics or so, you get entropy fluctuations, small, tiny fluctuations of the entropy. So the entropy doesn't always go up in a closed system or so. Yeah, and of course, the second law of traditional thermodynamics tells us that the entropy strictly increases. Yeah, now. So TP star is the theory with the little fluctuations, and TP is the strict law also, and they are strictly, they are strongly analogous or so. Yeah. And that does the job. So he uses this term strong analogy, and it was criticized. It's of course context dependent. Yeah, you may want to zoom in and care about the fluctuations, in which case you are not happy with the reduction. So in that case, the second law of traditional thermodynamics would simply be wrong. But for most practical purposes, also it's all fine and under control. So that's what Nagel did, and here is a little schema. Schaeffner did. Here's a little schema. So the idea is you have this corrected theory, and you have this notion of a strong analogy. All this points already in the direction that deduction is not so important anymore. Yeah, first they introduced approximate deduction, and in a second step they also felt the need to introduce this notion of a strong analogy, so which is also a non-deductive notion. So we see already, if one wants to make the Nagel-Schaeffner model or Nagel account of reduction more precise. Okay, so the starting point was the BCS theory of superconductivity, and the main idea was that electrons in a superconducting material condense into pairs, so-called Cooper pairs. Cooper pairs are bosons, so they can all be in the lowest energy state and sort of travel through the lattice of the corresponding material. This condensation happens at low temperature, and one needs a certain energy to break a Cooper pair. That's called the energy gap. Later formulations showed that we can explain this phenomenon of superconductivity by referring to what's called dynamical or spontaneous symmetry breaking. So the ground state of a system has a different symmetry than the generating dynamics. In this Nobel speech, Jonah Larsignou motivated it by this example that Nambu gave earlier. So you have a stick, it's rotationally symmetric. Now you put pressure on the stick, and once the pressure you put on the stick is above a certain threshold or so, the stick will bend arbitrarily in one of the directions. So it's not clear in which direction it goes. Each direction is equally probable or so, but this ground state that obtains after putting pressure on, and the pressure is also symmetrical, breaks the rotational symmetry. Yeah? So the bent stick is not symmetrical anymore. Yeah? So the idea is you start with a theory which has a certain symmetry, but the ground state breaks that symmetry. And the same happens here. There is a so-called U1 symmetry in superconductivity. It breaks the ground state. Doesn't have that. And what Nambu and Jonah Larsenio did is they basically transferred the corresponding symmetry mechanism or so to a new domain. They also changed the symmetry group that's broken, but the central mechanism is the same. Yeah, and that's what happened in that model. Yeah, as I said, they wanted to explain why protons and neutrons have certain masses, pretty high masses, and pions have a very low mass or so. How could we understand that? And they came up with this Hamiltonian. You don't have to understand the details, but it's a Hamiltonian that is chirally symmetric. It has a certain symmetry that is realized, but if one applies that Lagrangian, that theory to a particular physical situation, one sees that the symmetry is actually dynamically broken. So what one sees is, in this Lagrangian, one starts with a low mass term here, which could also be zero. But if one applies the theory, one sees that a mass is dynamically generated once this coupling, that's the interaction term here, once this coupling is above a certain threshold, which I normalized here to 1. So a mass of these elementary particles is actually generated once the interaction is above a certain critical threshold, and that kills the chiral symmetry. So you start with a chirally symmetric Lagrangian or so, but once the coupling is above a certain threshold or so, this symmetry is broken, which is manifested by the existence of this generated mass or so. Yeah, so that was the original Nambu-Jonah-Larsenio model, which was a nice little toy model in the first place, exemplifying dynamical chiral symmetry breaking in the domain of hadron physics or so, and that was already interesting. But later it turned out that there is actually a strong connection between the Nambu-Jonah-Larsenio model and quantum chromodynamics, which came in the early 70s or so, and which we now consider to be the fundamental theory of quarks and gluons, which establish the interaction between the quarks. Quantum chromodynamics also has this chiral symmetry. It's a chirally symmetric theory like the Nambu-Jonah-Larsenio model. And it was then possible to reformulate the Nambu-Jonah-Larsenio model in terms of quarks. Yeah, before it used to be formulated in terms of proton and neutron fields, and it was then reformulated in terms of quark fields or so, and the symmetry group was SU2 left times SU2 right. Pions turned out to be the Goldstone bosons, as we now say, that result from this dynamical chiral symmetry breaking. So the connection between QCD and the Nambu-Jonah-Larsenio model was not that it could be, the model could be deduced from quantum chromodynamics. It was more like that it shared lots of, it shared this central mechanism of dynamical chiral symmetry breaking with quantum chromodynamics. And people then extended it, make it more complicated. So it's now considered to be a low energy approximation to quantum chromodynamics, which is pretty similar to the relationship between thermodynamics to statistical mechanics, which also doesn't work in all cases. Yeah, I mentioned already in some situations we may be interested in entropy fluctuations, in which case we can throw away standard thermodynamics or so. But the claim then is that the NGL model reduces in some sense to QCD, despite it is not possible to deduce it. Yeah, so the NGL model cannot be deduced from quantum chromodynamics. People tried it, but that doesn't work. But at the same time, they share the identical mechanism or so of spontaneous chiral symmetry breaking. And what people also did is they matched the parameters. You have coupling constants and so forth in the Lambo-Journa-Larsenio model in a way that the empirical predictions turn out to be correct. Yeah, so there is this matching thing. Yeah, that parameters are fitted such that the two theories are compatible and produce the same empirical, measured empirical consequences. And that also led to the observation that the Lambo-Journa-Larsenio model carries much of the explanatory burden of QCD. Yeah, one of the issues with QCD is that in the low energy domain, it cannot be solved analytically or so. Perturbation theory doesn't work. So one has to do numerical simulations, so-called lattice gauge theory computations, which basically function like a black box or so. Yeah, so you tell the computer what you want to find out, and the computer computes for 2 days, and then it spies out a number or so. That doesn't sound like a good explanation or so. The Lambo-Journa-Larsenio model is much easier. It's sort of visualizable and so forth. So in terms of explanatory power also, the Lambo-Journa-Larsenio model is independent and has an important function in the research process. Now, it's tricky to actually say clearly how it relates to QCD. It certainly works well in the low energy domain, but it misses also one important feature that QCD has, also in the low energy domain, which is confinement. Yeah? QCD tells us that quarks cannot be found in isolation or so. They are always part of protons, neutrons, pions or something, but we cannot, they are confined in a sphere or so, or somehow with other quarks or anti-quarks. And that's a phenomenon that the NGL model doesn't account for. In a way, the NGL model puts all its weight on dynamical chiral symmetry breaking, so it sort of allows us to study the consequences of this one important feature of quantum chromodynamics, but it turns out that one gets pretty far with that. Anyway, my claim will then be that that's an example of a reductive relationship, yeah, but at the same time it's an example of a non-deductive reductive relationship. Yeah, there is simply no way to derive, even with bridge laws and approximations and so forth. That all this leads nowhere. But analogies play an important role here. Yeah, so I would like to say goodbye to this strict requirement that deduction or approximate deduction is central to our understanding of what reduction is. So I want to challenge the deductive paradigm that I think is closely related to logical empiricism, which has many merits and everything, but they stressed the role of deduction in science, and perhaps we can defend or identify a softer model of reduction. Yeah, so now if we want to soften the relationship between the reduced and the reducing theory, we may think of correlations or so, but correlations, if we model them by subjective conditional probabilities or so, that's probably too weak. It's just a kind of a association. So we need something more substantial than just correlation or so. And that's where analogies come in. Yeah, so the move I'm making here is that analogies, in particular material analogies, play a crucial role here. Yeah, we saw already that analogical reasoning played a role in the development of the original Nambu-Journal-Arseneau model. Yeah, the idea was to take over a mechanism that was understood or formulated in the BCS theory of superconductivity, and analogical material and analogies also play an important role in the full Nambu-Journal-Arseneau model. Yeah, so the idea is that there is a certain mechanism that is at a crucial position in the reducing theory and in the reduced theory that is doing the main job here. And in our example here, it's the mechanism of dynamical spontaneous symmetry breaking. I mentioned already this notion of material analogy. To understand better what I mean here, it's a good idea to contrast material analogy with formal analogies. So a formal analogy would simply be a mapping of mathematical structure. Yeah, so yesterday Karen, I think, spoke about LC circuits and the pendulum or so. So it's an instantiation in each case of the harmonic oscillator or so. Or we have Coulomb's law and the law of gravitation, which are instantiations of 1 over r square law or so. So arguably there is no connection between those instantiations or so, and that's basically the idea of a formal analogy. It's a mathematical structure. When we talk about a material analogy, we transfer a mechanism. Causality often plays a role. So there is something substantial going on. That's still not a very precise definition, but I think the contrast to a pure formal analogy is important here. And in general, I guess there is a continuum between formal and material analogies. It kicks in, the formal stuff somehow kicks in or so. So it's, I guess, maybe can discuss this later, but I guess there is no strict categorical distinction between the two. In any case, I would like to argue that the analogy we have between the NGL model and QCD is a material analogy, and so it's really a mechanism also that we find here and that we find there. That QCD exhibits this mechanism is supported by lattice calculations and other evidence. And in the case of NGL, it's clear because the model is basically that mechanism in vitro. Yeah? So analogies here, I think, are not only heuristically important, but also substantially, because QCD confirms that this mechanism is really in place. Yeah, so we know dynamical chiral symmetry breaking is actually happening, yeah, in QCD and in nature, and the NGL model exhibits this mechanism. It's plugged in. Yeah, it doesn't have to be explanatory. Lina yesterday spoke about explanatory transfer. And I think it's enough to have a confirmed mechanism. It doesn't necessarily have to be explanatory. Anyway, so this new model of reduction, analogy-based reduction, then looks like this. I think three important elements needs to be stressed. First, there has to be a material analogy between the reduced and the reducing theory. Second, the parameters have to be matched. So we want that the reduced theory accounts for the relevant phenomena the reducing theory also accounts for. So we just have to match the parameters accordingly. And autonomy is an important issue. That is, the reduced theory retains significant epistemic virtues, most importantly explanatory power, without direct reference to the reducing theory. And arguably, all these three conditions are satisfied in our case study, as I argued before. Now, I would come back to my functional twist, so to speak. Yeah? Why reducing one theory to another? And I before identified three functions, yeah? Consistency, explanation, and confirmation. And all these three functions are actually satisfied in our case study. So there is consistency. Yeah, we have the same mechanism at work. So the story, why is this or that the case, is identical or almost identical. And we have these matching conditions that is on the numerical or observational level or so. There's consistency. Then we have explanation. So the success of QCD provides additional justification that this mechanism of dynamic hygrosymmetry breaking is at work, and that supports the NGL model. It also goes in the other direction, and the NGL model also has considerable explanatory autonomy, because QCD is basically a black box in the low energy domain. And then we have confirmation and coherence, which is already plausible given that we have still both theories around. Yeah? So it's not that the NGL model or so is eliminated. People are still using it now also in hot and dense matter calculations and so forth. Yeah, so I think that stresses already the coherence claim I would like to make. Now, I would, having established the NGL model as one important case, yeah, and I think there's other cases that exemplify analogy-based reduction. Yeah? So there's always this issue of generalizability from cases or so. So of course more work needs to be done, but the NGL model is a pretty clear case. Now, analog black hole considerations don't quite fit this model, but there are interesting connections. What we have here is we have one common phenomenon type. Yeah? The phenomenon type is Hawking radiation, yeah? Which is instantiated in totally different physical systems. So we have it in black holes, for example, yeah, which are governed by GR and QFT and so forth. We also find it in Bose-Einstein condensates. So it's really a phenomenon which we find in totally radically different physical domains. Yeah, what we have is an analogy. Yeah. So Jeff also yesterday stressed many times the importance of the horizon. Yeah. So you need a horizon and a couple of other things, and then you get your Hawking radiation. Matching is violated because in the case of black holes, we are speaking about observations on black holes, yeah, and in Bose-Einstein condensates, you simply observe something else. So there is absolutely no matching of anything or so. And autonomy or so you have, the systems have independent explanatory power. Yeah, but matching, they are simply talking about different local phenomena. Now, when it comes to the functions of a reduction relation, there is a consistency, so there is no interpretive conflict or so. Explanation is an issue which is not so clear. Do we really explain what might be going on in a black hole by understanding what's going on in a Bose-Einstein condensate? I'm not sure. Confirmation, coherence is a debatable topic, as we discussed also yesterday. I think tiny bit of confirmation in a Bayesian sense is plausible simply because the two theories are analogous to some extent, and if you confirm one, then because of the similarity or so, something swaps over, but it may not be terribly much. The interesting thing here is probably that there may be a way to carve up the world totally differently or so. That is, one could start with certain phenomenon types or so and build theories around that. Yeah? At the moment, we have theories like GR and quantum fluids and so forth, and it's interesting to observe that they all exhibit this phenomenon of analog of Hawking radiation or so. Yeah, and Silke spoke about her instantiations, and we saw that there are 20 others or so. It might be, and there are many instantiations of harmonic oscillator phenomena or so. So it may be interesting to come up with a totally different account of the world and build them around those new phenomena. So in any case, things are theory or language dependent or so. When we talk about reductions or so, and I think this case of analog black holes sort of forces us to think about really how we want to carve up the world. And that's what I actually find one of the most interesting things we can learn from this. Okay, anyway, I'm running late. Here is my one-page summary outlook. So I hope to have convinced you that analogy-based reduction is a new model of reduction. So it contains the spirit and satisfies the function of a reductive relation, but it's a non-deductive model. Yeah, a model where deduction plays almost no role. I'm stressing it perhaps a little. It's characterized by three elements: analogy, matching, and autonomy. Counts as a reduction because it satisfies the functions of a reductive relationship, and I illustrated it by looking at NGL QCD and the relationship between these two. Lots of things to do. Further case studies needs to be done to show that it's not a one-hit wonder thing, yeah, that it also is instantiated in other cases. And it would also be interesting, alluding to what I said at the end, to sort of provide a bigger philosophical framework, maybe in the context of Ontic's structural realism also, but that's future work. Thanks.
Okay. Thanks, Stephan, and I apologize for the microphone. There is a question from Vincenzo.
Thank you very much, Stephan. It has been really very, very interesting. I have many very small observations. One is that for understanding in an intuitive way the point of breaking of spontaneous breaking symmetry, I think that the example of the Mexican hat is better than the stick, because in the stick there is some external energy. On the contrary, it is kind of spontaneous breaking of symmetry are always in the ground state. So the Mexican hat is very clear in the sense that going down you can make in many different ways that are equivalent from an energetic point of view. I think it is better. For me, it's more intuitive. Okay.
I think you are right. Nambu used it, and
yes, but
Jonah Darsinho in the Nobel lecture.
I know.
So I thought it should be good enough.
I listen at the same, but I find misleading.
You need the external force, but the external force is at least symmetrical. So
there's something. Second, there is this very beautiful book by Rocco Gaudenzi about, perhaps you know, about it is a study of the example of Nambu and
he was in Milan.
Okay. Yes. Now. Yes. He presented in Milan. Third observation. It's more general, and the concern what you said at the beginning, that is that you are looking for an image of science that is not reductionist but not completely patchwork like art, right? Okay. And indeed, my strong feeling is that you, in a sense, propose again something very similar to what in the Middle Age was analogia entis, in the sense that perhaps you are not speaking about something that is a reduction between theory, but you are looking for something that is for avoiding what Cartwright is making, that is the patchwork, completely separated, an equivocal in Middle Age term image of the being, without going in a monistic, univocal image of being. In a sense, you are proposing something similar to analogia entis, in the sense that there is something similar that could be in very different part of reality, and so perhaps it is perhaps it is not a kind of reduction. It is kind of partial unification between different realm of phenomena. It seems more similar to what Thomas and in general Middle Age, because in Aristotle approach, you know, there is this plurivocity of the being, but he attempted also to say there is something common, that is the substance notion. This does not work indeed, but it is possible to speak about an analogia entis in this new and different way. There is something, a very big project in a sense.
Thanks. I guess what I want to do is I want to avoid simple accounts. So the unity of science account is very simple. You need 2 sentences to explain it, and we can all sort of relate to it somehow. And the radical pluralism is also a very simple story. Yeah? Now life and science is complicated. Yeah. And I think there is lots of interesting intertheoretic relationships which we as philosophers should classify, discover, and examine also from a normative point of view. Yeah. So the rest of my talk was just a contribution to that project. Yeah. And I identified this one of probably many different types, and I wanted to argue that it's we can call it a reduction, yeah. But there may be much, and I'm sure there is much more, and other types of intertheoretic relation may also be normatively justifiable. What I think is the general main idea is that I think coherence plays an important role. Yeah, so I think what we want is a coherent account, a coherentist account of science. We want that things hang together nicely, but not in a strict deductive way or so, but more like established via, I don't know, plausibility, explanatory, and whatever types of relationships. Yeah, the more ambitious project for me as a Bayesian is to reduce it all to subjective probabilities, but that's more farther away. Yeah. So I mean, what the example you gave also sounded like something where people put everything on one card or so, and I'm a total pluralist there. Yeah. So maybe I'm a second order pluralist, and Cartwright is a first order a pluralist. So that would be the difference. Yeah.
Giovanni or Lina, I don't know who is the first yesterday. Giovanni?
Okay, hi Stefan. Thanks
Hey.
for the talk. Yeah, so I'm very sympathetic with the idea of adding an element of analogy to the reduction program, and also to the idea of not having a deductive form of reduction, but rather a non-deductive. And in this sense, analogy being a non-deductive form of inference should help. However, I would like to understand a bit better your idea of using analogy in this analogy-based model of reduction, because I think I try to myself to think about that, basically starting from the Nagel-Schaffner model that you worked on in the past. There is, I think, a sort of prima facie tension between reduction and analogy in the following sense. So analogy is usually between two systems, the target and the source. And then you can have models of both and find relations between them. But the idea is that you have these two systems, and based on their similarities, one would like to infer that additional properties that we find in the source are also present in the target. When we talk about reduction, we're really looking at one system, and we have, say, two theories that at different levels try to describe the same system. In the case of the ideal gas, you have statistical mechanics at the micro level and thermodynamics at the macro level, but that you have the very same system. You just have different theories that try to describe the same system, but analogy, as I said before, involves two different systems, source and target, and perhaps different accounts of them, different models. So it's not entirely clear to me what kind of analogy can help in the case of reduction. At some point, I thought maybe Stephan is going to insist on structural analogies, formal analogies, but then instead you invoke material analogy as the requirement for having a successful analogy-based reduction of one theory to another. So I would like you maybe to clarify this a little bit, especially in light of this prima facie tension that I spelled out.
Okay, good. Yeah, thanks. Yeah. So we have an analogy here between two theories. Yeah. So NGL and QCD are analogous because the same mechanism or so is instantiated in both, yeah, but both are different or so, yeah. So maybe the source target language is not appropriate here, yeah, which is perhaps more important in heuristic contexts or so, yeah. You understood the source and you would like to learn something about the target or so, and so you transfer it. Here we have two scientific theories. One is more fundamental than the other, but both at crucial parts instantiate this model, yeah, or this mechanism or whatever, yeah, and that establishes the analogy. It's material because it's a mechanism. We have independent evidence for it. It's not just a 1 over R square or something, a kind of thing. Yeah, reduction, as you rightly say, somehow is one directional or so. Yeah, one is more fundamental than the other, but that we have in this case here. Because, I mean, I mentioned the matching conditions, yeah? So in the domain where the two theories overlap or so, we make sure by fitting the parameters that they coincide in terms of predictions and so forth. But QCD is more general and is so that breaks the symmetry there. Yeah. So yeah, the source target thing is not working here. But I would still talk about an analogy here and perhaps suggest to liberalize the language.
No, I agree. It's not just a matter of language. I mean, literally, in one case, we have two systems that we compare. In the other, we have one system and we try to describe it differently.
But
so
two
it's
theories,
more than just language.
Yeah,
Sorry?
we are talking about theories here. Yeah, so there is an analogy between two theories, not between two physical.
Yeah, exactly. We need to have like maybe a notion of theoretical analogy or something like that. And one last point, just to make sure I understood. So in case of the Nagel-Schaffner model, we do have analogy between TP and TP star, namely the phenomenological theory to be reduced by by TF, the fundamental theory, and the corrected version of it.
Yeah.
In your model, the analogy
there
is
is
between
no TP star. Yeah.
there is no TP star. So the analogy is between TF and TP.
Yeah.
Okay.
Exactly.
Good. Okay. Thanks a lot, Stephan.
Good to see you.
Good to see you too.
Lina, please.
Thank you. So I have two questions, so I'll try one if I can. And oh yeah, I enjoyed the talk very much, I should say first. Thank you. That's very, very interesting. So I'll ask one question first, and then I don't know who else is holding a hand up. So just to let you know, I'll keep my hand up, and if we have time, we can come back to my second question. So the first one I wanted to ask is about your discussion of analog black holes. And the claim that it violates matching, so that we don't have a matching requirement, so that we're not fitting parameters. Now, one thing that I wonder about that is, well, kind of how much we should think about that as being something that really is peculiar to analog black holes, or how much of that we think is peculiar to a kind of Hawking radiation case. So if you think about the kind of analog gravity and cosmology research program more generally, I was thinking of cases where it looks to me like people are trying to do exactly those kinds of things. So I have in mind the Cambridge group working on false vacuum decay, trying to calculate parameters for bubble clusters and bubble decay rates to apply to early cosmology. And my sense is that this is not something kind of intrinsic to the analog program. It just, it might be a feature of certain aspects of it being applied, but that is kind of contingent on our current level of access rather than any. So I sent in the chat there just a reference to that paper I had in mind. So I'm wondering how deep that violation really is. And that makes me wonder whether or not there is scope on your account for thinking that many of these kinds of cases are going to be analog reductions in your sense, since the explanation ones seem to be up for grabs more on your view.
Thanks a lot. That's very interesting. I need to look into this. I mean, I had this naive picture in mind that people like Jeff are talking about Bose-Einstein condensates, and they measure things on Bose-Einstein condensates, and then there's black holes, and it's probably different. We can measure. There's even nothing to match. So now there's at least measured. So, but I'm very interested in this, and so maybe one can push the things a little further here and explore to what extent analogy-based reduction could illuminate those investigations. Yeah. So thanks.
Oh, thank you very much. No. And if there's people waiting in the room, we should move on to another question. Otherwise, I'll leave my hand up.
Last question, Simone.
Thank you so much, Stephan. It was brilliant. I will say I absolutely agree that we should seek other kind of scheme of reduction to account for the scientific inquiry in general. I just have a question that pertains to the last point that you mentioned in your last slide. Specifically to, the notion of emergence, because I know that you're talking about reduction, but I had just a general curiosity about if in your new framework you are also considering some robust definition of emergence, or you have more a strategy that is similar to the one that Nagel had. So reduction, you just define emergence in contrast to reduction. So where you have a failure of reduction, that you have some sort of emergence, but I was just wondering whether you are just also working toward some sort of robust notion of reduction, of emergence, sorry. So thanks.
Yeah, thanks. I haven't thought about.
Yeah,
it's okay. Yeah, thanks. I haven't thought about emergence in this context. Yeah, traditionally, I thought that emergence is just a negation of reduction, but then Jeremy Butterfield came and told us that they can all live happily together, or so. So it might be illuminating to think about it in this context, but I haven't done so yet. I was happy to say something about reduction. Thanks.
Okay, thanks again, Stephan. Next speakers are Vincenzo Fano and Marco Sanchioni.
Thank you very much, Marco. This is a work in progress, both mine and by Marco Sanchioni. And indeed, the first result of the work is quite different from what we put in the abstract. So do not look at the abstract now, because it's completely different from what we concluded working on on this topic. I have not slide because I don't like very much this kind of presentation. I hope that I will be enough clear in presenting only speaking. Perhaps I will write something about what I am saying in this blackboard that we established now. Okay. First point is that we are working on one other kind of analogy that is very relevant in the topic of black holes. That is not the analogy between experimental analog with black holes like Bose-Einstein condensate, on which yesterday we spoke a lot, but on the fact that in general in the 70s, Bekenstein, Hawking, and many other worked on the physics of black hole inside the framework of general relativity, finding that there is a strong analogy between black holes and thermodynamic system, classical thermodynamic system. So here is something very different, is also an analogy. There is a paper by, I don't remember the name, in this volume edited by Vera Matarese and many other people that is possible to download online in philosophy of astrophysics in general. There was also Nora Boyd that worked in this book, and you can find this paper. I don't remember the author, but it is this paper is about Mati. The name of the author is Mati. But the paper is on the fact that indeed working on black holes, there are two analogies, very important analogies. One is the one about which we spoke yesterday, and the other one is the one that we are speaking now about. Okay, so and these two kinds of analogies are strictly connected in the sense that one is connected to the other. Okay. Working on this topic, we noted a very important point that here we are in a context in which the normal schema of an analogical reasoning, that is, perhaps I can write something even if it's not so important. You have, there is, as you know, there is a target object. There is it's very difficult. I am not very able to work with this. There is a source object, and you know that there are many different features that are characteristic of the source object, and you find the same characteristic in the target object, and the next one should be the same. This is a very simple presentation, very typical presentation. What is a analogical reasoning? Here is the situation is quite different. It's quite different. Why? Because here we are not speaking about this kind of stuff. We are not speaking about an analogical reasoning based on a set of properties that are very similar in two different systems, physical systems, and this similarity in a certain sense justifies the fact that the next one justify or make plausible that the next one will be also very similar, even sometimes the same. It's different. Why? Because this kind of analogy is an analogy that grounds the whole research program. Indeed, when we speak about the analogy between black holes and thermodynamic system, classical thermodynamic system, we are speaking about something that is at the base of a general research program began in the 70s, as it still now is very fruitful, very important, so more than 50 years long. And so the situation is quite different. We cannot apply what we learned, and we learned a lot about analogy in the case of analogical reasoning. we should say something different. There is something different from an epistemological point of view when we speak about the analogy in a research program. We look a lot in the literature, and we found a few very interesting observations about analogy in research program by Paul Barta in his wonderful book of 2010, Paralleling Reasoning, in which he dedicated not a lot of space, but few pages on the problem of analogy in the research program. He spoke above all about mathematics, indeed, but I think that something could be similar in physics. And the fundamental point of the reasoning of Paul Barta about this point is that we should pay a lot of attention. We should pay a lot of attention when we use an analogy to ground an entire research program. Why? Because the problem is that when you use analogy in analogical reasoning, if we don't found what is plausible, the analogy say to us what is plausible to find, okay, is in a sense a sort of element of the logic, presumptive, alleged logic of discovery. It justifies us to look for something, okay? But if we don't find the analogous, the game is over. Okay, there is no problem, no possibility to make very big mistakes. On the contrary, when an analogy is at the base of an entire, a whole research program, the situation is more difficult. Why? Because this analogy is part of the glasses through which we look at reality. So this is the point by Paul Barta. Not only by him, he quoted Stephan, I think is the name of a philosopher who spoke about this problem. These glasses could be so strong that we don't see that this research program is completely wrong. So the situation is different from a rational point of view. Okay, I will say something about this fundamental point. Okay, now we come back to the analogical reasoning, and it is very easy to find in the realm of analogical reasoning very reasonable heuristic rules about this notion of plausibility. Plausibility in the sense of Paul Barta in general, my feeling, our feeling when we see about this notion is that plausibility is not something probabilistic. You cannot ascribe a probability to a sentence that you consider plausible, but is a modal notion in the sense that if you consider the set of the possible world, or the physically nomological possible world, plausible means that that P is plausible, means that there is a meaningful percentage of the possible world in which P is true. Okay, you don't know which is this percentage. You know only that is not without meaning. Okay, so it is only plausible. Is a very generic notion with a part of justification value. It's not something completely only heuristic. And also Paul Barta in paper successive to his book, he considered, he allowed that this kind of possibility is real, that so that analogy is not something only in the logic of discovery, but also something that could have a bit of justificatory value. In the preceding talk by Steve Hartmann, he said that in a sense it is analog, it is experimental analog of black hole, could have a bit, very thin quantity of confirmations. Confirmation is a relative notion, so it is not necessary that confirmation by this experimental is big. It's very teeny, it's very small, okay? And indeed, if we accept, this is our reasoning, if we accept that in the discovery, analogy plays a role, making something plausible, it is impossible to say that analogy is completely devoid of justificatory value. So indeed, analogy is always something rational, partially rational. Okay, is strongly fallible, this is clear. Okay. Second point, we have rules. We have rules about how, perhaps it's better to say one thing before, that the notion of plausibility is graded. We have degree of plausibility. We cannot ascribe probably a number, a metric to the plausibility of a sentence, but we can say that something is more plausible that another item, that something on the basis of a bigger evidence is more plausible than what was with a smaller evidence. Okay. If plausibility has degrees, we have also rules that govern these degrees. We can say the first rule is that clearly bigger is the number of features that are common to the target and the source, and bigger is the plausibility. This is a very, very obvious rule. On the contrary, bigger are the differences between the characteristic of the target and the source, and smaller is the plausibility that the next property of the source will be also a property of the target. Here comes a very important point in our research. Indeed, this second rule about the degree of plausibility of a thesis, in the case of a research program, if we consider that in the research program there is the danger we spoke about before, that is that a research program could be not only something, a research program based on analogy, could be not only something that propose plausibility and we control the result, is something more, something more. The analogy is in a sense supportive with respect to the whole research program, and in a sense the analogy say to us what to see and what don't see about the experimental phenomenological situation. So here we should pay a lot of attention to differences, okay? Here we propose a different principle from what is normal in the case of analogical reasoning about difference, that if we find a difference between the two items of analogy, source and target, that is meaningful, this could be enough to put in discussion, to call in discussion the whole research program. We should pay a lot of attention, more attention, this is an epistemological point, a very important one, about differences in the case of research program. Normally, differences clearly decrease the degree of plausibility. This is clear. Here, an important disanalogy could be something very important, very meaningful in accepting or not the general research program. Okay, take for example the case of ether in the analogy between fluid dynamics and electromagnetism that was very fruitful, and people thought, also Maxwell thought, that this vibration of electromagnetic waves were vibration of something exactly like the vibration in fluid dynamics, waves in fluid dynamics. They look for this kind of stuff. They found that this kind of stuff does not respect Galileo invariance, and all this, you know how the story finished, in the sense that was the breaking of the analogy and the breaking of the research program of thinking electromagnetic waves as a sort very similar to what are waves in the case of fluid dynamics. So you see that one only difference is enough to put in discussion, to call in discussion a whole research program. This is very important, and it is something different from what happens in the case of the plausibility of an analogical, of the conclusion of plausibility in an analogical reasoning in a smallest, in a more local kind of situation. Okay, we used formal, material, formal, and functional analogies, in a sense a bit different for what was used before. I don't know which is the correct use of this term, because everyone uses a different way, but we distinguish three levels, okay? The material one for us is substantially what concerns the features, okay? If the features of the target are the same as the features of the source, this is a material analogy, okay? I don't know if it's correct, but it is the terminology that we used in this draft of the paper. Second level is when you have also an explanatory analogy, in the sense that the theory which explains the target is not completely, but almost the same that the theory that explains the source. And in this case, probably you have also a functional analysis, in the sense that the mechanistic, the causal nexus that govern the two items, that is source and target, are similar. You can also have a formal analogy, and normally formal analogy and functional analysis are together, not always. You can have situations in which formal analogy and functional analogy are real, but are true, but not material, in the sense that the peculiarities, the characteristics are a bit different, are really different. On the contrary, the form is similar. For instance, think about Fokker-Planck equation and Schrödinger equations that are very similar from a formal point of view, but indeed we are speaking about something completely different, and many other cases in physics are very common of this kind of situation, in which you have formal analogy, sometimes also functional analogy, but you are speaking about something strongly different. So material analogy is not present. Okay, so three levels: material analogy, formal analogy, the mathematical model is similar, functional analysis, explanation, the causal mechanism is similar. Okay, it is clear that here we have principle, very simple principle about the degree of plausibility. More kind of analogy you have, better is, more plausible is the conclusion, okay? Passing to the case of research program, the situation is a bit different, in the sense perhaps it's better to speak not of plausibility, like in the case of analogical reasoning, but the capacity to support the research program by a fundamental analogy. So we can speak about the supportive character of an analogy is something different to what is the case of analogical reasoning. And in a sense, when this analogy is supportive with respect to a research program, we can say that is also the research program is also promising. Perhaps the fundamental point is that the research program is promising, in the sense that if it is a good analogy, the research program is promising. You will find something new, something interesting. It is not completely, but partly different from what happened in the case of analogical reasoning. Much more dangerous. When analogy is used in a research program, is much more dangerous than in a local, single situation in which you have a target, a precise target and a precise source. Here you have something much more bold, much more difficult to treat, and so we should pay a lot of attention. Okay, I think that these are the fundamental instruments of the kind of investigation about which we are interested. That is the case, I remember to you, the case of the analogy that ground an entire research program about black holes that was proposed in the 70s and arrived until today. That is the idea that black holes are thermodynamic objects. So now we can apply this kind of approach, this kind of a general approach to the single situation about which we are interested. Okay, in the 70s, Bekenstein discovered that there are a strong formal analogy between black holes on one side and thermodynamic system on the other side. There was also a very important difference, in the sense normally thermodynamic objects radiate. On the contrary, black holes do not radiate. Okay, as you know, a couple of years after, Hawking found that applying both general relativity and quantum field theory in a very peculiar way, a very original and creative way, you can find that also black hole radiates. So the analogy began to be stronger. Okay, what seems at the beginning a big and important difference that could put in discussion, call in discussion the entire research program was confirmed, it was found by Hawking. It is very interesting to read the papers of Bekenstein at the beginning of the 70s, because you find that for him, the analogy between thermodynamic objects and black hole was very strong, was a fundamental point about his research program on black holes. Okay, so it is very, very important. Consider also that in the 70s, neither general relativity, neither quantum field theory were confirmed theory, indeed. As you know, only in the 80s, general relativity became a really accepted theory in the community of physicists. There is this wonderful book by Will about the accepting of general relativity in the 20th century. It shows that only in the last decades of the 19th century, general relativity became really a part of the toolbox of physicists. On the contrary, as you know, quantum field theory was formulated, the standard model was formulated indeed in the 60s and the 70s, but also this kind of theory was accepted very slowly. So, and it became something definitive only with the discovery of the Higgs boson in 2012. So you see that the paper by Hawking was a big bet. He took to very, very speculative, very audacious, very bold theories like general relativity and quantum field theory. He put it together and found something completely new about black holes, confirming the research progress, the intuition by Bekenstein. That is, that you can find a strong analogy between black holes on one side and thermodynamic objects on the other side. Okay, at this point there was a new problem, a big problem, that is, the information paradox. According to the calculation by Hawking, the evolution of black holes, that is, the radiation of black holes, is not unitary in the sense of quantum mechanics. But you know that in classical thermodynamics, all the processes are unitary. If I put the journal, the secret journal of Karen in a fire, it is possible from the ashes and the smoke, it is not easy to do, but it is possible, to build again the journal of Karen. There is nothing that is, there is no kind of loss of information, okay? All information is conserved. That is, the process is unitary. I remember to you that unitarity is a mathematical notion, but I remember to you that unitarity is a very important notion from philosophical point of view. Unitarity means that if you have two different physical situations, it is impossible that they go in the same physical situation. Because if it happened, it would be a loss of information. On the contrary, the journal of Karen, the secret journal of Karen, it is something peculiar, something unique that you can build again, rebuild from the ashes and the smoke. Okay, so unitarity is a very important notion from an ontological point of view, not only from a physical point of view. And Hawking radiation is thermal. That is something without information. So all information that were important in the making of the black hole, for instance, the star from which the black hole come, would be lost. And this is not unitary, and this is not thermodynamic. So here again, we have a strong disanalogy between what happened to thermodynamical system and what happened to black holes, okay? You know that people worked a lot. There is this wonderful book with plenty of remembering of history by Leonard Susskind, The Black Hole War. I advise to you very much. It's a wonderful book that tells about his history until Hawking, at the beginning of 2000, that is 30 years after the discovery of the information paradox loss, the information loss paradox, he accepted that indeed he was wrong. Okay, that is, quantum mechanics unitarity is not violated in the case of black holes. But at the moment in which I think 2008 was 2005, I don't remember exactly the year in which Hawking accepted the new idea about black holes. But indeed, at the moment, it was not completely clear how to find the information that was lost. Okay, only in the 20 years after this accepting by Hawking, physicists, theoretical physicists, has been able to find how to find this information. You know, it is a very long story with a lot of steps, very interesting, very important steps. And the last step of this story is the papers by Pennington and collaborator in 2019, 2020, in which he showed that indeed, after a certain time in the history of the evaporating black hole, and this time, as you know, is the page time, the radiation is, and the new radiation is entangled with the past radiation in a way that keep information. So in a sense, it is possible to, even if it is very difficult, indeed it is impossible for asymptotic observer to relieve this kind of information. Anyway, from a physical point of view, in this new form of calculation, it is different form of calculation of Hawking radiation, the information loss paradox is, in a sense, solved. Okay, this is a very important step in the physics, in theoretical physics in the last years. Sorry? Yes. No, but your journal was in a fire. Here the point is you put your journal in a black hole. It's quite more dangerous. Okay. Anyway, here you see that the thermodynamic program at the beginning of the 70s had another victory. Okay, it is a very important step in the history, and you see that there is something strongly progressive. Okay, in introducing how much time I have? 10 minutes. Yes, in 10 minutes are enough. Okay. The notion of progressive research program is very important. Why? Because it is clear that not only a grounding analogy is fundamental for research programs. Research programs are something that were proposed by Imre Lakatos, and Imre Lakatos established also, he explained many details about the research program. You know, research program is an attempt to propose a sophisticated logic of discovery against the Kuhnian Feyerabendian point of view that is completely anarchist. Also against Popper that proposed a too rigid kind of logic of discovery. On the contrary, research program is a sort of smooth, of mild logic of discovery. Okay. And he proposed also criteria to establish whether a research program is progressive or regressive. The criteria are two, very simple and very reasonable. A research program is progressive if it is able to produce new theoretical results, and it is progressive if both are sufficient, if it can has confirmed novel prediction, confirmed use novel predictions. That is, predictions that has unexpected and are confirmed experimentally. The second criteria is not so important in our case because the story of the application of this analogy between thermodynamics and black hole physics is above all a theoretical story. But you saw that it is what I said is enough to see that in this 15-year-long story, there has been many important theoretical results. Bekenstein analogy, Hawking radiation, Pennington calculation. These are perhaps the most important three steps, but there are many other important positive results. So we can say that the research program based on the analogy between thermodynamic object system on one side and black hole on the other is progressive independently of the role of the analogy, of the epistemological role of the analogy. Okay, here we should apply the fundamental principle on which we emphasized before. What? The fact that in the case of analogy that is fundamental for research program, we should pay a lot of attention to differences. And you saw that, in a sense, all three important theoretical results I presented are all results that eliminate an important difference between a thermodynamic system on one side and a black hole on the other. Okay? Indeed, there are two obvious senses in which black holes are different from, for instance, a vapor engine. Okay? One is that the vapor engine is not a quantum mechanical object. The second is that the engine is not, the vapor engine is not a general relativity object. It is clear that speaking about black holes that are solution of general relativity, we should modify, adequate the rules of thermodynamics to this new case, this general relativity. Okay, but it does not propose so big difference that we are compelled to throw the general research program. Concerning quantum mechanics, here the situation is quite different in the sense that we discovered the thermodynamic peculiarities of the black hole exactly you thinking about black hole, as Hawking proposed, as quantum mechanical object. So this difference is, in a sense, exactly the fuel for the analogy. Okay, so we can, the point should be studied more clearly, but the fact that black holes are quantum mechanical and general relativity object does not seem enough to say that this analogy is wrong. Okay, anyway, we should think more on this point. So if we should not apply the principle that a research program based on an analogy should be abandoned or called in discussion in the case in which there is a meaningful difference, we can make a step forward. And this is the bet of physicists today, I think. And it is very important from an epistemological point of view to see that as philosophers, we can understand a bit about what is happening in physics. Which is the point? The point is that making this kind of calculation, not only classical thermodynamics was used, but also the notion of entropy. But not only the classical macroscopic notion of entropy, but also the von Neumann entropy, which presupposes that there is a sort of average, a sort of calculation on microstate. You know that entropy is not only something that was introduced in the first half of the 19th century to understand the functioning of an engine, but in the second half of the century was shown that by Gibbs and Boltzmann that entropy indeed is a particular number connected to the microstate of a thermodynamical system. And indeed, we can speak about what happened in a thermodynamic object, speaking with entropy in this second sense as a sort of parameter strongly connected to the number of microstate and the probability distribution of microstate, also in the case of Gibbs. Okay, so all the analogy is strongly presupposing that black holes are not only thermodynamical objects, but they are also statistical objects. Okay, statistical mechanics objects. This means that the next step is to find the microstates that are at the basis of this entropy. Okay, so now we are betting, and people that are working on this topic is betting that the analogy is working, that analogy is not wrong, that the research program is still fruitful, that there are not so big difference to abandon the research program. And so we are brought to the conclusion, see, this is something that concerns not analogical reasoning, but something that concerns the favorability, the positivity of a research program, something different. It is an analogical reasoning, but an analogical reasoning is supporting a research program, not a single case. It is saying that this research program is promising, and it is saying that now we can look with great interest to find which are the microstates in the case of black holes, on which the entropy is the von Neumann entropy of this calculation. This is a bet. This is a reasoning that today a lot of physicists are making. We think that is a kind of reasoning that epistemology should investigate and think about. Thank you very much.
Thank you, Enzo. We have a few minutes for some brief question. Karen, and after Francesco.
Yes, thanks very much. There's a lot that you're saying that I agree with, and I like, as you're saying, that it's progressive, it's allowing us to make these predictions. But at the start of the talk, you were saying, from Bartha, that when we are looking at whole research programs, it can be quite dangerous because it's like the glasses we're wearing that stops us from seeing that it might not be correct, right? And then I was interested because you say, and here, I disagree about the plausibility. Yeah. So the plausibility aspect, yes, I agree. The plausibility, the analogy can make things plausible, but not in a way that we believe it. Like, it's not a confirmation plausibility, it's a heuristic plausibility. It's giving us something to explore. And I think this became clear from then what you said in the rest of the talk, that the analogies, for them to be useful, heuristic, to help us make these predictions, it doesn't require that the source or the target actually be correct. Your example with the ether was very nice. It was very heuristically useful, making developments, and then it turned out to be false. So, yeah, I think it doesn't require the confirmation aspect. And I agree with you with this, the black hole case. Yeah, it is progressive, it's heuristically very useful, but not with the confirmation aspect, more like, let's explore this. Yes, thank you.
Thank you very much, Karen. We are very happy that you agree with us, because we are a bit afraid that we are speaking about something completely wrong. The danger is always that we are saying something completely silly, and if you agree, we are very happy, I think. Thank you very much.
Francesco Nappo.
Thank you. Thank you for the talk. One thing I was wondering, so in the book with Giovanni, we distinguish between two ideas about confirmation by analogy. One is confirmation by similarity, and the other one is, I think, what you're talking about, which is confirmation by theory building or model building. Okay, so just forget about confirmation. But what I mean is we leave it open, let's say, for somebody to say that there is a qualitative important distinction between analogical reasoning in the ordinary sense and the analogy that goes on in building a model or building a theory or building a research program, etc. Okay, so that seems like what you're trying to say is that there is two different types of considerations involved in these two cases. Okay, my let's say response on the from the perspective of somebody who wants to say, oh, it's the same thing, would be to say that in one case it's just the stakes that are maybe higher or lower, but it's the same reasoning.
Yes, sure, yes,
right?
yes.
So the criteria are the same,
yes.
but
Yes.
maybe from the perspective of communication
Yes.
or the perspective of like betting on particular kind of research. Yeah, that more pragmatic aspect rather than the logical aspect of the research.
Yeah, very similar. Yes, I agree completely. Indeed, in the draft of the paper that we wrote in these days, there is only a very small difference in the criteria. The fact that on the basis of the difference, we should give much more negative epistemological value, but all the rest is very similar. Yeah, I agree. It is different, the context. The context is different. It deserves attention, both from a historical point of view, both from epistemological point of view. Indeed, Barta was very afraid. I understood, because there are very wrong research programs like female and race. So he say indeed there are analogies in these cases, but this analogy bring us completely astray. So he's very afraid of the use of this kind of reasoning. So he leaves completely out from his book. But I think it is necessary, because it is perhaps it is the most important theoretical project today, Marco, I think, and so it is an example. So we cannot live in physics. Indeed, I understand that in other context is a kind of research program is very dangerous. Okay.
Maybe I can have a follow. So, I mean, this there's a sense in which this point by Kuhn that at the beginning of the research program there's always going to be a lot of anomalies and differences, right? And so, isn't this kind of risking to make any sort of research program sort of never take off the ground if you care so much about differences, right? If you care so much about, So I wonder how you would. I mean, I agree with the methodological point of being very careful.
Sure. Yes, this is a very important point. Yes, you are right. Indeed, it is true. Because yes, I forgot to say that it is one of the peculiarity of this approach is that we are speaking about analogy, not in an admitted that the difference between revolutionary and normal science has sense. That is not sure, but indeed a bit of sense has. Probably it is a blurry distinction, but it is important from epistemological point of view. Indeed, at this point, we are studying analogy in the case of revolutionary science, not in the case of normal science. This is much more difficult. And indeed, we all agree with Kuhn and Lakatos in saying that what is peculiar of the revolutionary science, but indeed perhaps also in the case of normal science, that the theory lives in a sort of sea of anomalies. And this is, from a logical point of view, is a very delicate point of view. And a very delicate problem, because indeed when you use analogy, it is very dangerous. Okay, yes, we should think about. Thank you very much.
Okay, I don't see other questions, so thank again, Vincenzo. And okay, we can start the last talk by Francesco Nappo from the Polytechnic University of Milan. And the title is Falling In, Analogy or Universality. Please, Francesco.
Okay, thank you so much. Thank you for the invitation. I think we should thank really much Giovanni for having organized this. So thank you so much again. Very nice hospitality. Okay, so today I'm going to be discussing some work in collaboration with Niccolò Cangiotti, who's a colleague of mine. So I mean, I'll be returning on the issue of analog experiments and what they tell us. Okay, so I think this is the conference main topic, and so I'll try to provide in this talk I'll try to provide in part a defense of the approach that Niccolò and I have been developing over these years, but mostly I would say a defense of the distinctiveness of this approach relative to the other accounts out there in the literature. Okay, so that's the job that I will try to undertake. So if we think about the epistemology of analog experiments, in particular black hole analogs, I think there's a short answer. Okay, there is a short answer that we can give about their significance, their meaning. Okay, which goes something like this. Okay, so the first thing is that regardless of whether these experiments say anything about Hawking radiation, okay, these experiments are revealing some relatively surprising properties about the system on which the tests are occurring. So they're revealing surprising properties of, for instance, the behavior of Bose-Einstein condensates or the behavior of surface water waves. And so they're helping to, maybe devise new types of explanations and generate new physics in general. Okay, so I think this idea of model knowledge, okay, that you get some more knowledge about the physical systems that you're testing on. And I think this also resonates with some of what Professor Jansson was saying yesterday in her talk. Now, the other thing that we can say, I think safely, about the epistemology of analog experiments is that if you hold certain kind of moderate to high standards for evidence, for evidential support in physics or in science more generally, then very likely, okay, what you observe in analog experiments is not evidence for Hawking radiation in black holes, okay, because there are so many differences to consider. And if you hold relatively high standards for evidence, then it's, you may end up with an idea that, okay, so yeah, so they're interesting in some sense of the term, but they're not evidence. Now, I take, so I read the paper by Karen et al. In roughly this sense. So I take it that they're holding some relatively high standards for confirmation in physics, for what confirmation means in physics, and they're denying that there is confirmation in that sense. Other people who hold sort of similar high standards for evidence in the literature are people like Peter Arkenstein, who thinks that confirmation is tied to there being more evidence than not, right? Or even Rovelli, who says we should be very strict about when we talk about confirmation in physics, because confirmation in physics should mean absolute confirmation. Okay, let's not talk about incremental confirmation because, in the Bayesian sense, because that's dangerous to physical practice. So this is the short answer, let's say, okay? Now, let me try to give an account, let's say, of what people like Dartashti, but also Stephan and also Niccolo and I are thinking about, okay? And I'll try to sort of think of this in the more general background of discussions about non-empirical assessment. Richard David and others, and we actually discussed this with Stephan this morning. I think non-empirical assessment is not a very felicitous term. Maybe we should talk about issues of indirect evidence, as was suggested by Stephan. But I'll use non-empirical or semi-empirical assessment as the kind of home where these discussions can take place, okay? So the idea is that, well, in addition to, let's say, direct evidence and direct observations and direct experiments, part and parcel of the physicist toolbox today is also non-empirical methods of assessment, okay? So the idea is you evaluate a theory or a prediction partly based on indirect sources of evidence. Of course, David has given an account of a few of these sources of indirect evidence, but I don't think they're exhaustive. And the case of analog experiments kind of, I think, shows that there is more variety to non-empirical assessment methods than what's recognized in these works. Why should we want a theory of this kind? Why should we want to talk about non-empirical assessment? Well, because in a sense, we're doing epistemology. We're trying to understand what perhaps is the difference between scientific expertise and other kinds of expertises. And part of this job may involve giving an account not just of the official science that you get from textbooks and papers, okay, but also the unofficial science of doing science, of researching. And so in part of this, this may involve giving an account of expert judgment, okay, the kind of expertise that will allow a researcher to distinguish between a promising from an unpromising research project even before you subject your hypothesis to test, okay? So I think that's an important task for epistemology. Of course, you cannot undertake this task if you have very narrow understanding of evidence, if you hold, for instance, that evidence is tied to severe testing or to absolute confirmation. You need to couch the sort of epistemological talk about expert judgment or plausibility under a more liberal sort of evidential umbrella, okay? So, a candidate for this would be Bayesian confirmation theory, just because it has this incremental aspect to it that's helpful. But there are other views out there that are similarly liberal in this sense. And it's exemplified, I guess, this non-empirical assessment by the use of the Hawking radiation as a kind of a benchmark for a theory of quantum gravity. Okay, the idea is we get quantum Hawking radiation from a variety of distinct plausible models of cosmology. So the prediction is in some sense robust to the choice of model. But this is now also taken as some kind of a benchmark for evaluating plausible theories of quantum gravity for the future. Okay, so that's, you can see that it's in a sense very theoretical, very indirect, but it's still something that drives people's, physicists' judgments about what's plausible to expect about the future. Now, so now that we've sort of tried to couch the projects that I think people like Radin and Stephan, but also we are trying to conduct. Let me just say something more specific about the case of analog experiments, which is the fact that, the analog experiments have to do mostly with the idea of assessing or evaluating a prediction, okay, rather than a theory. And the prediction here is Hawking radiation, or at least a radiation effect with certain kinds of specific physical properties that would make it like the derivation in Hawking's paper. Now, here's I think, in particular, where we should place the significance of analog experiments, and I think this is agreed upon by everybody in the debate, is the fact that an obstacle for Hawking's prediction is the Transplanckian problem. Okay, it's the idea that the outgoing modes or particles are coming, if you trace the histories back into the distant past, they're coming from, in Hawking's semi-classical model, they're coming from ultra-high energy regimes, and the fact that relativity is supposed to not hold that those energy regimes generates a problem for the prediction, because it sounds like the model is sort of self-undermining in some sense, right? So we cannot trust the prediction in this sense. So Unruh comes in at this point, and the way I understand the research program is to say, okay, sure. Look, in the case of fluids, okay, if you think about the analog simulation, in the case of the fluid, you make the fluid act as if it's gravity, and sound as if it's light, okay? In the case of a fluid, of course, there is fluid dynamics, which is continuum, and it predicts, in a sense, ultra-high energies at the micro scale, micro with the I. But we know from the atomic theory of matter that, roughly speaking, at some point there is a cutoff, which is a natural cutoff, such that the energies will at some point end in quantum stuff, in quantum mechanics, and so the idea is, can we test this prediction in the case of sound, so that we will at least know what happens in the fluid case, right? So I apologize. So this is terribly simplistic, but the idea is, well, you have, let's say, in this case, you have the semi-classical model. Don't care about the specific scale here. The semi-classical model, I take it as somewhat plausible, even though we don't know if it applies to black holes. And then you have Hawking's prediction, right? So that's the idea. I think that's more or less the situation as I'm picturing it, right? The difference between the gap between the model and the prediction here is due to the fact that there is a Transplanckian problem. It's due to the fact that there is an obstacle in deriving the prediction from the model, which is that we have to assume that Transplanckian regimes don't mess up the derivation. Okay, so and again, the way I think we should think about this idea of confirmation is that once you get confirmation that in the simulation the prediction is verified, then you should be somehow try to drag your confidence in the prediction closer to that of the model. Okay, so that's at least the way I'm thinking about the case, right? Once you've removed an obstacle, then you should think that the confidence in your prediction is sort of closer to that you hold into the model, right? And so this also reflects a bit the judgment of people like Unruh, okay, who says, this is a recent paper explaining a bit the whole research program. It says, well, the reason why we're interested in analog simulations is that if you could show that for dumb holes, the existence of the changes of the theory at short wavelengths did not destroy the existence of thermal radiation from a dumb hole, right? So in the sonic case, one would have far more faith that whatever changes in the theory of quantum gravity created whatever nonlinearities quantum gravity introduced into the theory, the prediction of thermal radiation from black holes was robust, would be robust. All right, so I think this is the sort of the idea. Okay, so you got the prediction, but you know that's subject to an obstacle. But then if you can somehow test an analog, then you can drag your credence in the prediction a bit further up. Now, what I'm going to do now is to say that once we start thinking about the epistemology of black holes in this way, black hole simulations in this way, there are two alternatives. There is a crossroad, okay, to take, and a choice to be made. Right? It's a bit like the Beatles and the Rolling Stones. Okay, so I will try to list some of these differences, comparing in particular the account that Niccolò and I have been developing, mostly from inspiration from Hesse's work on seminal work on analogy in science, and I will compare this to the prominent alternative by Dardashti and others who are coming from literature on universality in in scientific explanation, right? And specifically, I will focus on the view that Dardashti and others defend in their published papers, and so to try to say that there is a distinction between these versions or these stories about the epistemology of black hole simulations. Now, as I understand, Dardashti and others are accepting the role of analog experiments in what here I'm calling non-empirical assessment. Okay, so they're thinking of this in terms of some kind of indirect evidence or confirmation, but they reject the so-called face value interpretation, the idea that, as we saw before, it seems sort of natural to think of Andrew's argument as a type of analogy, as making a kind of analogical inference. If the classic situation would turn out this way, then it's plausible that the quantum case will also be similar. So they reject the analogical interpretation, at least as I'm thinking of this. The inspiration for their account comes from appeals to universality in the philosophical literature on scientific explanation, people like Batterman and others. And in a way, the account that they defend is the idea that once, if you think about the epistemology of black hole simulations, you should consider the fact that there are universality theorems or universality results available in that domain of black holes, and they are the sorts of results that they need in order to ground the evidential status of black hole simulations. Okay, so you have the fact that, first of all, you have available certain kinds of analytic results to the effect that Hawking radiation is multiply realizable. Then you have also the experimental confirmation that, in fact, Hawking radiation occurs in a diversity of analog experiments. Okay, so that's I guess the second component. And now the equation is saying once you have this variety and you have the fact that analog experiments are multiply realizable, okay, then you can construct a Bayesian argument as to why observation of a new instance of Hawking radiation in the analog domain can be evidence or confirmation for Hawking radiation in the black hole case, in the real target case, right? And this goes basically through evidence that Hawking radiation is a universal phenomenon. Okay, this view is actually then roughly, you find the same sort of view in other papers by some of the co-authors, okay, Tebol and Hangleiter and others. Now, I guess the shortest way of explaining our viewpoint on the subject, or alternative viewpoint, is the fact that we also are accepting the experiment's role in sort of non-empirical theory assessment or prediction assessment, but we are trying to defend the face value interpretation. We should think of these as analogical inferences. So that's I guess the shortest way of saying this. In a way, this is a way also of pointing out that among the various methods on non-empirical theory assessment and prediction assessment, analogy plays an important role. The idea that Niccolo and I are trying to develop is that, in fact, we should not think of analog experiments are based on the availability of universality results, but rather on material analogy, on the fact that you somehow you are assuming in the situation the existence of certain kinds of macro level or kinematic similarities, that even though in a sense they are in a certain respect light similarities, because you don't have matching in the dynamics, you don't have matching in the micro physics, you know, they are significant enough for granting certain kinds of claims about the you know, the dragging of the prediction in the good cases. Now, and this is the point about material analogy that we're trying to develop. Why is this a material analogy? What we mean by this is not that obviously the you know, that analog experiments are made of the same stuff, the same material as black holes, because they're not. But what we mean by this is that you know, you can think of some of the similarities in the situations as things that you can accept sort of before and independently, right, of any analogical inference that you are going to build up through the engineering a black hole analog. Okay, so some of these similarities are established sort of rather independently of your attempt to engineer a black hole analog. So this is the Beatles theme here, but the idea is I'm going to discuss now 4 differences, like the 4 Beatles. Okay, so the first difference between these accounts is ground, the physical basis. Right, the physical basis, according to the Dardashti et al. Account, the first difference is, you know, the first central result here for evidence is this idea that there is a universality result, okay, and they point to various results in the literature, including this paper by Andrew and Schutzold, right, to the effect that Hawking radiation follow from a certain set of general and multiply realizable conditions. Then, at least in the 2017 paper, they also defend the idea that in order for there to be confirmation, you need an isomorphism, which I read as a kind of a formal analogy or one-to-one correspondence between the quantities in the models for, on the one hand, fluids, and on the other for black holes. And then the third thing is the idea that you also need a sort of diverse realization of analog experiments. So you need a sufficient, let's say, basis for saying that, okay, so actually, given the various experiments, analogs of Hawking radiation can be multiply realized. Okay. Now we are discussing this analogy-based alternative in rather different ways. Okay, so as I said, we emphasize the idea that the inferences are based on material analogy or material similarity, such as the fact that in some sense the geometry of the case is similar. Okay, that there is a similarity between light and sound, and for instance, in the fact that there is a limit, let's say, to the speed of light, like there is a limit to the speed of sound, right? And of course, also the similarity in the cutoffs. Okay, so the idea is you can build up an analogical inference on the basis of these similarities because we could recognize them already before we even started thinking about analog experiments. And so they're, in this sense, material. The other big difference with the universality view is the idea that it's actually some kind of robustness considerations that for us really are driving the inference. So it's mostly, I guess, although not exhaustively, the fact that it's the idea that you've seen before in the quote by Andrew, that the regularization of waves at the extremes, okay, so the extremes here being meaning near the horizon, are unlikely to differ much from the mode of regularization of the waves that we observe in the classical fluid case. Okay, so of course, in the classical fluid case, we know that there is a particular mechanism of regularization of the waves that is given by the molecular structure of matter. But the judgment that is really crucial to our assessment is the idea that whatever other mechanism of regularization occurs in the black hole case, this is unlikely to be much different from the one that we observe in the classical case. And there are, in the paper, the original paper, we also mentioned some of the results that make us think that alternative regularization mechanism for waves at the extreme would still give you Hawking radiation. Okay, so replicas. This is a joke on Paul McCartney. This is a replica of Paul McCartney. Anyway. So what's the other difference that I'm trying to point out? Okay, so it's the difference that according to the universality-based account, experimental evidence of Hawking radiation, the Hawking radiation is multiply realized, is necessary for an evidential volume assessment, okay? And there is a sense in which diverse realization, the capacity to support Hawking radiation in the black hole case is immediate, okay? In the sense that each observation of Hawking radiation in the analog experiment is some evidence for Hawking radiation. Right? Now, I'm trying to contrast this account with the analogy-based account, okay, in which, roughly speaking, we provide a different explanation of the variety of experimental realizations, okay? The physicists, in a sense, aren't trying to multiply experimental realizations to gain more evidence, okay, but the main explanation for why they're building up so many different realizations is that it's very difficult to get a really good high-quality simulation or high-quality realization of Andrew's design. Okay, so we have Andrew's design. That design stays in a relation of analogy with the black hole case, and it's just very difficult to reach an experimental result that is as clean as the one that we are imagining in thinking. Okay, so in a sense, one way of putting this that the role of diverse realization is in evidence is sort of mediated. Okay, so that you're trying to sort of cancel some of the experimental noise rather than trying to increase your evidence for Hawking radiation. What about, sorry? Yeah. So it has a role. So the realization, so a high quality realization of Hawking radiation in the analog case can confirm that in the classical situation, okay, the explanation for Hawking radiation, the analog Hawking radiation, does not have to be found in the high energy microphysics. It has to be found in maybe some factors concerning some facts about the physics of horizons. Okay, but I don't need, let's say, a lot of realizations to do this. I could just be satisfied with a very high quality one if there was one. Third difference, okay, potential. Now I understand that more recent papers, let's say by Dardashti and others, maybe have sort of smoothed out this difference, but at least the first papers that also Karen reacted to sounded like through the methodology of analog experiments, you really can get some substantial confirmation for black hole radiation, right? And so this is, for instance, something that Thibault also said in 2019, and I think it's partly also the spirit of your response to their initial paper to sort of smooth out a bit the enthusiasm on the subject. If let's say this is a way of thinking about this. Of course, our account is rather different. So we first part of this discussion is that we don't think that the universality-based results provided by the Dashtinal actually ground or justify the more exciting or enthusiastic assessments. Okay, so this is something that we can consider, but I think right now, most people that I've talked to sort of agree that confirmatory support is just incremental, is not substantial. But the other, and so this is the first thing. The other argument that we have is that, in a sense, once you have accepted that, you get just, this, the methodology that is based on universality is not, providing substantial confirmatory support, then you should at least consider an alternative analogy-based interpretation as sort of an equal footing, right? And so that's why we're developing this alternative. Final difference, recommendations. Okay, so this is another way in which I think we are differing. So if you think of, the arguments from, or the inferences from analog experiments as being, as turning on universality and so multiple realizability, it seems natural, and which is what also is done in this paper by Radin and others. It seems natural to think that, okay, so let's look out for Hawking radiation in relatively exotic physical systems. Okay, let's try then to multiply the types of physical systems in which materially distinct systems in which we can find Hawking radiation, right? And so, and it's actually an interesting also fallout consequence of the Bayesian analysis that they provide in this paper, that in fact exotic media or testing on exotic media gives you more confirmatory support than testing on more familiar media. Okay. Now, in our recommendation on analogies is sort of the opposite. Okay, so we're trying to say, well, we are just interested in a high quality realization of Andrew's experimental design. Okay, and if we look for a clean realization, one that sort of has very little noise, that you cannot explain by other effects other than analog Hawking radiation, okay, then it's best to actually test your prediction on a familiar physical media, one that you have good knowledge of, rather than an exotic one. And in a sense, the Bayesian analysis that we each provide can be seen as, let's say, trying to elicit this sort of disagreement in methodology. Okay, so falling in, I like this idea of falling in because it's a little bit about black holes. So now you fell in the let's say the whole of non-empirical assessment, and you've seen that it's a mess. Okay, so that maybe there are different views out there about what is the methodology of such non-empirical assessment, and so maybe the conclusion to draw from this is that it's too messy. Okay, that maybe it's too confused, or maybe one of us is wrong, and maybe we are wrong. But you could make at least a plausible argument, I think, that there is such a thing as the analogical interpretation. So I like this falling in also because I think in English, you also can say falling in as you need to take sides. Okay, you can take this side or take the other side. So in a sense, and again, yes, it's a bit like this. And so the idea is, okay, so accounting for the role of analog experiments leads to this kind of forking situation. Now, let's focus very briefly on their compatibility or incompatibility. Okay, so I think that the stronger version that of the universality-based account that I find in the papers by Vadin and others, okay, are incompatible with the analogy-based interpretation, in the sense that as I read them, they're trying to say that it's universality really the source upon which evidence, okay, flows from the experimental realization to the black hole case. So that view is inconsistent with the analogy-based interpretation, and in that sense, they're distinct epistemological perspective. They differ, as I mentioned, in ground, in role of replicas, in attributed potential, and in recommendations. Now, there is if you like, a smoothened out, a softer version of each approach, okay, that says, okay, so you have identified, each of you has identified a confirmatory effect, one coming from similarity, the other going through universality, okay, and in this sense, the two views are compatible, okay, but in order to do this, you will have to give up on sort of the idea, for instance, that you have a novel type of inference that confirmation via analog simulation goes through universality alone. Okay, you have to somehow find the place for an analogy-based interpretation. I mean, in a sense, what I'm going to say is that the situation, in defense of the non-empirical assessment people, that the situation in which you're in is not too embarrassing, that we have confusion or that we have disagreement about the methodology of non-empirical assessment, because, and we knew this all along from the problem of induction, right? In particular, the descriptive problem, that it's very hard to even find a coherent description of what the inferential practice of science is in the first place. And so I guess one of the methodological recommendations could be that of keep developing coherent epistemological alternatives rather than despairing because there is disagreement or seeming confusion. Right? And I think also maybe the presentation that we had yesterday by Professor Jansson and Professor Weinfurtner were maybe going, I guess, in the same direction of developing epistemologically coherent alternatives. Final thing that I would say is that, is that the case of analog experiments, especially the two accounts that I've provided here, could be a good case study to relate to the more general issue of indirect evidence or non-empirical assessment, because, Professor Richard David has has a list, let's say, of methods that are used in what he calls meta-empirical assessment, but definitely analog experiments or analogies are not within that list. And so it would be nice to try to show that analog experiments are within this broader family of assessment methods, non-empirical assessment methods. Okay, so that's all. Thank you so much for your attention.
Thank you, Francesco. We have time for some questions.
Thank you very much, Francesco. From your presentation, I understood something that to me was not so clear. I thought that the idea of universality was not so accepted in the context of the discussion of analogical reasoning. I remember that Mary Hessing, in her book, speak about this possibility, that is to find a common genus that is in a sense what make possible. It is a sort of disappearing of analogy in the sense that if you apply universality, in a sense, you are no longer speaking about analogy, but about something that is more similar to subsumption or something of this kind. And indeed, I understood that from your very detailed analysis that universality is indeed accepted by many scholars. In our presentation, the draft of our paper with Marco, when we speak about analogical reasoning, never we use the word the same. The same feature of the target, but always similar form, similar mechanistic. So our point is our presupposition, but at this point I understand it is not so obvious, it should be justified, and you work very well on this side. That it is not so obvious that all kind of bridge between target and source are based on similarity and not on identity.
Yeah, exactly. Yeah. So that is exactly right. So the idea is, at least as I'm interpreting the universality account, is that I mean, the paper, the initial paper by Radin was skeptical that we could get off the ground by just using similarity, because similarity is qualitative. It's, there's similarities and differences. And so the attempt, I guess, was to say, okay, so there's this common ground, and then we can establish an evidential channel through identity in some sense, right? But that has been criticized, and in the paper we sort of summarize some of this criticism that we agree with. Okay, so we agree with Karen, we agree with Grace Field on the subject. So thanks for the comment.
Karen?
Yeah, thanks. I mean, as you know, I'm very sympathetic, and I see clearly the differences between the two approaches here. But so are you now disagreeing with me? I'm saying we can have both, and you're saying that they're two distinct, that you have to choose one or the other.
You mean with your reason?
Yeah,
reason?
I'm being conciliatory.
Yeah, exactly. So yes, I'm saying that you could think of this situation also as one in which you have confirmatory effects that come from analogy and from universality. That's compatible.
Yeah.
That for all we say, that's compatible with our argument. And so you can have both in this sense, yes.
Oh yeah, thanks.
But you need to take sides, okay? If you think that there is there is a better and a worse way of, there's a better and worse notion of confirmation by analog simulation.
Yeah, and just on this topic, but I also have a more serious question, because I was thinking, we're talking about the meta-empirical assessment, but the way you're describing it, maybe this case, we can think of it as meta-empirical assessment, the fact that we have different ways of confirming it.
Yeah, exactly.
But, yeah, that's a bit silly. But my real question to you is, why are you relying so much on Hess's theory of material analogy? Because I think this is a weakness for your account. I can understand why you are doing it, because if you don't have the material analogy and it's just a formal analogy, then you're falling back into the universality reading, right? So the material analogy is important for you. But Hess's account requires these similarities, observed similarities, to be pre-theoretic. Right. And I think in this case, we don't have anything pre-theoretic. What did we see of black holes before theory? Nothing.
Yeah.
What do we see of dumb holes before theory? Nothing. So I think her account is maybe, you shouldn't rely on it so much. Maybe look at Barther instead.
Yeah. So the answer to this is that I've been interpreting Hess's distinction between pre-theoretic and post-theoretic in sort of a non-empiricist sense. Okay, so the idea is that you can shift. So as science grows, you can shift the let's say the boundary between what's pre-theoretic and what's post-theoretic. And so as the result of this, stuff like certain parts of general relativity and certain part of the language of general relativity becomes pre-theoretic relative to the others. And I think there is textual evidence also for this. So Hesse speaks in their book about the fact that when you have analogies in quantum physics, you can take the language of classical physics as pre-theoretic. And this, to me, this suggests that, in a sense, depends on the context, but if you speak
so maybe
to an expert,
yeah. Because she also says that like we can build analogies, right? So that
right, but that would introduce new language, that would introduce new terms, and so that in that sense would be formal or non-material, right? The interpretation part. There's actually a very nice paper now by Paul Franco from the US, who's an expert on the history of Mary Hesse. And it seems like at least, until the early work, she was holding on to this sort of more pragmatic view of what is the distinction between pre-theoretic and post-theoretic.
Okay,
So,
thanks. Yeah, I'll look at this because she's hard to read. I think.
yeah, she's very hard to read, but it's a wonderful paper on reference early works.
Thank you.
Yeah, thanks. This was very interesting and inspiring. Can you say a bit more? It relates to what Karen said in her first question about criteria for how to evaluate these meta-theoretical problems. That just doesn't seem to be a methodology or so, right? I mean, there is this universality model and there is this analogy type model and nice stories, both tell nice stories, but how do we assess them? Scientific models are evaluated in the light of empirical data also, but here it's hard, and I think that's really something that needs to be done because it's probably not so difficult to come up with just another model or so, and then what do we do here? Yeah, exactly.
Yeah. Yeah, well, yeah, great question. I mean, in a sense, you know, the question is that you can try to be, you know, you can take different positions between, you know, being fully descriptive and being fully normative, okay, and so it's difficult to even agree on the methodology here. But so I guess one criteria would be, okay, so what are scientists right now doing, okay, and what kinds of projects about analog experiments, for instance, they consider as the most valuable, okay, and so if they say, okay, well, let's look into exotic media, then it seems like a view like universality is more plausible, whereas if they resort to more familiar media, then descriptively it seems that, you know, the analogy-based account is more plausible because, you know, each of them has a particular recommendation that you can somehow test on what scientists do, okay? At the same time, you can also say the opposite. You can say, well, but I have a sort of a normative view, and so I think that scientists are entirely wrong about what they should be doing, and so I guess, I mean, you know, one tries to strike a balance, let's say, so that if they really are not interested in exotic media or they're really not interested in very familiar media, then maybe it's an objection to the account. But this is an example. I have to think about more.
The analogy, because we know by induction that analogies have been historically very successful. So that's an argument for your view. You're relying on analogy. We know analogies work in science, so maybe this is a possibility.
Right, yeah. So the idea is that, well, we have a lot more evidence of reconstructing cases of analogy than of universality, and so that's an argument for plausibility. At the same time, you can allow for the opposite viewpoint to start the reconstruction work that shows, in fact, that there are instances of the other kind. But yeah, so that would establish, let's say, a burden of proof on the other side. Yeah.
Lina and then Giovanni Valente for the last question.
Thank you. That was fascinating. I really enjoyed that. I wanted to suggest that there might be at least one distinction that might be helpful in trying to organize these views. And I think it might also connect to how plausible they seem in terms of getting to one of the questions that was raised just now, namely how we eventually end up comparing them, and if at some point we shouldn't end up at a position where we are appealing to empirical evidence in a fairly standard sense again. Because one thing that struck me when you were speaking is that if you read someone like Smith and Harper's account of Newton's methodology, on your way of thinking about it, this methodology would in some sense count as a weak notion of confirmation, but they would not have characterized it that way. In fact, they would have characterized it as an unusually demanding notion of evidential reasoning in physics stronger than standard Bayesian or hypothetical deductive accounts. Exactly because it builds in a certain forward-looking element. So those kinds of accounts have built in with them the idea that we should have resilience under small variations in the data. We should be able to handle deviations from idealization. So we commit our theory to a certain kind of research project going forward of accounting for the problems that we might encounter. And it has a certain self-correcting element built in because all that success is very non-trivial. So we also have some promise of actually being able to identify where the theory starts to fall short if it does. And all of this is very different from an idea of evidence where you think that you're just doing a one-off test, and if the theory is rejected, now you go back to scratch and come up with a new one. Right? This is a really kind of different starting point for thinking of setting up a forward-looking research program. So this was a long way of introducing the fact that I was going to say the one way of trying to start to categorize and evaluate the different methodologies might be to look at whether they are primarily forward-looking or backward-looking. So are they concerned with the evidence that I have at the moment? Or am I concerned about how I'm setting myself up to be in a better position in the future to get the kind of evidence that I want to have? And which one are they weighing most highly? Because those seem to play out slightly differently even in these cases. So here you might correct me. You might not be thinking about the model this way, but my kind of immediate reaction was to think, well, look, part of these analog reasoning is partly looks more amenable to future-looking projects, while the kind of universality argument is very much concerned about the evidence that we have at this moment. So how am I evaluating the plausibility of the theory at this given moment with the universality arguments I already have, the data I already have, but less, it can say something about what other evidence might raise that, but it's less concerned for giving me a research program going forward. That's just not what it's in the business of doing. So in some ways, they look like they have different goals, which means that they might not be so incompatible. After all, they're asking slightly different questions. Even though we can get to a tricky case, which is the one that I think would cause potential difficulty, is when, if you wanted to evaluate a Newtonian research program, you then ultimately are going to ask about what evidence you've accumulated over centuries for supporting the theoretical framework. So you are at some point, of course, the evidence is going to come in or fail to. That's the hope, right? Eventually. At that point, we're going to have very different judgments. But at the stage when you're setting out the kinds of non-empirical, meta-empirical criteria that you're concerned with, you can also have a difference in what you're focusing on, evaluation at this moment of the probability or the likelihood, if you want, or the future-looking prospects for gaining more evidence.
Yeah, thank you so much. This is very helpful. So let me say that I can confirm that in a sense, the account that Nicolò and I are developing is inspired by this sort of forward-looking idea of, you base your reasoning on an assumption or a presumption or some kind of expectation of uniformity between the classic and the quantum, and then you build off of that together with the existing similarities. Okay, so I can confirm on my side that there is definitely this forward-looking aspect going on. I'm a bit more, let's say at the moment, I don't have enough to say whether, we could entirely classify universality in sort of the backward-looking sense of evidence, but I don't know, maybe there's comments on this, but it is, let's say that at the very least, it is the way I was reading the papers as well by Radin and others, that they were a bit more concerned about what you discussed as the backward-looking sense of evidence. So thank you for this.
Okay, the last question, Giovanni, please.
Yeah, thanks, Francesco. That was really clear, really good as usual. So I'd like to make a comment, but I should make a disclaimer to begin with. Namely, I lost 5 minutes or missed 5 minutes of your presentation. So my comment might have already been said by you. And so I'm not adding anything, but just maybe reiterating a point. So I think that a crucial difference between universality reasoning and analogical reasoning that is worth emphasizing rests on the inferential process behind the conclusions that we make. And that's where the role for induction that you invoked in the last slide would come in. So in an analogical inference, the premise is the similarity between source and target. And from there, you conclude in a non-deductive way that there will be an additional property common to the two systems that we can attribute to the target. And so that's where the induction comes in the conclusive step. In a universality argument, instead, your premise is systems belong to the same class of universality, and then by deduction, you reach the conclusion that similar or maybe the same type of phenomena occurs in the systems in that class. So, but that's a deduction. So the inductive step is what enables you to establish the premise, namely that these systems belong to the same universality class. And so I think, from the point of view of the inferential practice, they're rather different forms of reasoning. And that's where the role of induction sits in both cases, In the conclusive step for analogy, in the premise of belonging to the same class of universality, in the other case, namely the universality reasoning.
Yeah, no, thank you. This is
something that squares with your view.
Yeah. So it does. So it's very helpful actually because it is a difference, let's say. Now, having said that, so in the paper we do say that. So we do compare, let's say, the universality-based account to a form of, enumerative induction. Okay, you reach a bunch of instances to get the generalization, and then you deduce the new instance from the plausibility or the probability of the generalization. But I don't know to what extent this is something that we can say it's agreed upon as the description of the inferential practice. So maybe speaking of enumerative induction is a bit too harsh, but I agree that this is something to consider, just exactly where the inductive step is. So thank you so much for that comment.
Thank you.
Yeah.
Okay. Thank you again, Francesco. And just a few words for the concluding remarks by Vincenzo. Thank you to you all.
Thank you to everyone for this small but wonderful congress. We learn a lot about analogy and about black holes that are so mysterious and fascinating objects in physics, and probably new physics will come from black holes. So we are taking part to a very interesting and very important scientific adventure that is comprehension of this very particular, very peculiar kind of stuff that is black hole. Thank you to all participants from far and near, to people coming here in Urbino and speaking about this interesting topic. Perhaps I can give the mic also to Giovanni, the principal investigator of the research program financed by the Ministry of the University here in Italy about analogy in science, and the the unit of Urbino was about analogy in physics. Before this, I would say that we are thinking about, Giovanni and myself, about a small book in which people that took part to this Congress, not only you, but perhaps also some other, can prepare a very, not a big paper, but a short paper that could be in a sort of introduction, not popular, but of a very high level popularization of the problem of using analogy in black hole physics, a sort of instruments for the general reader that would be interested in understanding these fascinating objects and the importance of analogy in this context. We are thinking about, and we will contact you probably about this project. Thank you very much again.